Hello grade 11, welcome. In this video, let's talk about the Earth's internal heat, and that includes the geothermal gradient and the convection current, and also the radioactive decay. Tara! Our discussion will focus on the learning competency, describe where the Earth's internal heat comes from. At the end of the lesson, you should be able to 1. Describe the chemical composition and temperature of the layers of the Earth. 2. Explain the mantle convection as a way of heat transfer. And 3. Recognize the importance of Earth's internal heat. Earth receives heat from the Sun, but aside from the Sun's heat, we can also feel considerable amount of heat coming from below emanating from deep within the Earth. This heat also drives important geological processes such as the movement of tectonic plates and the flow of magma near the surface of the Earth. Earth can be divided into three main layers: the core, the mantle, and the crust. Each of these layers can be further divided into two parts: the solid inner core and the liquid outer core, which are composed primarily of iron and nickel. The upper mantle, which is partially molten, and the lower mantle, which is the liquid portion of the mantle. These are composed of iron, magnesium, silicon, and oxygen. The thinnest and the outermost layer of the Earth is also divided into two. We have the oceanic crust, which are composed primarily of basalt, and the continental crust composed of granite. Earth's temperature increases with depth but not at a uniform rate. This is called the geothermal gradient, which refers to the rate of increasing temperature with respect to increasing depth in Earth's interior. Earth's geothermal gradient is 15 degrees to 30 degrees Celsius per kilometer within the crust. This figure shows the geothermal gradient in each layer. As you can see in the graph, the temperature gradient within the lithosphere varies depending on the tectonic setting. Gradients are lowest in the central parts of the continents, higher where plates collide, and higher still at boundaries where plates are moving away from each other. The Earth's crust has an average thickness of 8 to 40 km with an average temperature of 14 degrees Celsius. These temperatures vary. For example, in coal mines situated at a depth of 1.5 km, the temperature is about 36 degrees Celsius. In some South African mine, the temperature at a depth of 3 km is 50 degrees Celsius. At certain kilometers, the temperature is as high as 200 degrees Celsius. Below the crust is the mantle, which has an average thickness of 2,900 km and has an approximate temperature of 3,700 to 1,000 degrees Celsius. In here, the geothermal gradient remains below the melting temperature of rock, except in the asthenosphere, where rocks are softened and become plastic. Gradients then drops off dramatically through the mantle and increases more quickly at the base of the mantle. Below the mantle is the outer core, which has an average thickness of 2,250 km and has an approximate temperature of 6,100 to 4,400 degrees Celsius. Since iron melts at 3,000 degrees Celsius and nickel at 2,900 degrees Celsius, the outer core is molten. And at the center of the Earth is the inner core, which has an average thickness of 1,300 kilometers and an average temperature of 6,000 degrees Celsius. But why is the inner core solid? The reason is the great pressure at the center of the Earth, reaching 100 billion pascals. The pressure forces the iron and nickel atoms together, keeping them in crystalline form despite the high temperature. Convection helps to move heat within the Earth. Convection current refers to the continuous loop of sinking hot soft rocks caused by energy transfer in the asthenosphere. Convection creates loops of sinking and rising materials in the mantle. This circular pattern is called convection cell. This carries heat to the surface of the mantle much faster than heating by conduction. A convecting mantle is an essential feature of plate tectonics. Convection in the mantle behaves the same way convection happens in a pot soup on a hot stove. The material near the heat source becomes hot and expands, making it less dense than the materials above. Buoyancy causes it to rise, and cooler materials flow in from the sides, then sinks at the bottom, creating cycles of the sinking of cold and rising of warm water. And this is how convection happens in the Earth's mantle. There are two major sources of heat, the primordial heat and the radioactive heat. The primordial heat comes from the word primordialis, which means of the beginning. This refers to the heat from accretion and bombardment of the Earth during the early stages of formation, or when the Earth was formed. A major source of Earth's heat is radioactivity or the radioactive decay. This refers to the energy released when the unstable atoms decay. The radioactive isotopes of uranium-235, uranium-238, and thorium-232 in Earth's mantle are the primary source. Radioactive decay produced energy in the form of heat, and the heat generated reaches the surface of the Earth. Now let's discuss the importance of Earth's interior heat flow. 1. Formation of surface oceans and surface continents caused by tectonic activities. Because of convection in the Earth's mantle, tectonic plates in Earth's crust are able to move, creating both surface oceans and surface continents. The combination of oceans and continents established the biogeochemical cycles that allowed Earth's surface temperature to be sustained at an optimal level for life in spite of the ongoing brightening of the sun. Number 2. Earth's strong magnetic field caused by the solid core. The Earth's unique, strong, enduring interior heat flow enables it to have both a solid inner core and a liquid outer core. This creates magnetic field that shielded Earth's surface life from deadly high-energy particles flowing in from the sun. And that ends our lesson. I hope you learned something today. Congratulations!
Kick.